Hello everyone, I'm Jeong-sik Choi from Seongkyungwan University. Thanks for having me. I'm happy to attend this NVMSA conference. Today I'm going to talk about our paper presented at Ugenix ATC. The title of the paper is Live NVMe-IO, Reconstructing Software I/O Paths with Failure Atomic Memory Mapped Interface. As you may know, software overhead is now greater than storage latency. Storage devices are getting faster and faster. As a result, the software overhead has taken up the significant percentage of file I/O. So our goal is to minimize the software overhead on low latency, non-volatile main memory systems. To reduce the software overhead and to fully exploit the low latency NVMe systems, we reconstructed software I/O paths with a library that we designed, called Live NVMe-IO. This library performs user-level I/O. It runs on any file systems that provide DEX/mmap. It transparently intercepts I/O requests and turns them into memory-mapped I/O operations with logging. When an application calls fsync, it atomically writes logged data to the original file. Before fsync, logged data is not reflected in the original file. Live NVMe-IO aims to make the common I/O path efficient. It handles data operations at the user level, but metadata operations are routed to the kernel file system. It provides low latency scalable I/O as well as guaranteeing data atomicity. Our goal is to provide low latency and scalable file I/O while guaranteeing data atomicity. We have carefully made design decisions to achieve these goals. First, kernel level I/O versus user level I/O. We choose user level I/O. In low latency NVMe systems, user level I/O is better than kernel level I/O. As you know, kernel's I/O stacks introduce software overhead, so we use memory mapped I/O to perform user level I/O. Memory mapped I/O can access files directly with load store instructions instead of read write system calls, so it can reduce user kernel mode switches and avoid kernel's complex I/O stacks. Once the mapping is complete, it does not require indexing and permission checks. As far as we know, in low latency NVMe systems, memory mapped I/O is the fastest way to access files. Logging is more efficient than copy and write in NVMe systems. Ensuring data atomicity requires a recovery mechanism, so we need to choose between copy and write and logging. Copy and write dramatically increases write amplification. It usually performs writes at page granularity. Even if only a few bytes are updated, the entire page must be written. It cannot take advantage of the byte addressable NVM. Moreover, the use of huge page is increasing, which makes copy and write more expensive. If copy and write is used for memory mapped files, TLB shutdown occurs every time a copy page is created. It adds significant software overhead. Logging techniques require writing data twice, once to the log and once to the original file, which may cause software overhead, but it can log at byte granularity. It's called differential logging. It has less write amplification than copy and write. Besides, read logging allows checkpointing out of the critical path of execution, since read logs have durable data. So we believe that the logging technique is more appropriate for byte addressable, low latency NVMe systems. There are two logging policies, redo and undo. Which is more efficient? Most logging systems employ only one of them. However, each logging policy has different strengths and weaknesses depending on the access type of files. For example, When an application writes data to a file, undo logging first copies the original data to the undo log. After the log becomes durable, it writes the new data to the file in place. On the other hand, read logging first writes new data to the read log. After the log becomes durable, it overwrites the data to the file. Read logging allows writing the file out of the critical path of execution. Since the read log has the durable data, the writing can be performed in the background. Therefore, read logging is better for writing. When an application reads file data, read logging requires reading data from both the file and the log to get the latest data. On the other hand, undo logging can read the data directly from the file without checking the undo log, since the latest data is always in the file. Therefore, undo logging is better for reading. To take advantage of both logging policies, we use adaptive policy depending on the access type of files. We call this hybrid logging. Read-intensive files use the undo logging and write-intensive files use the read logging. To trace the access type of each file, hybrid logging maintains per file read-write counters. It determines the logging policy on each fsync. Hybrid logging can achieve the best case performance of two logging policies. Logging systems can adopt centralized or decentralized logging. Most modern systems use decentralized logging for scalability. However, libnvmmio uses a centralized logging with fine-grained logs for efficient and scalable I/O. Decentralized logging techniques were designed for transactions. It's easy to support isolation. For example, per thread logging and per transaction logging. However, general file I/O is different from transaction. It does not require isolation. When a thread completes writing, other threads must be able to see the latest data immediately. When a thread reads a file, per thread logging has to check all logs to get the latest data. On the other hand, centralized logs have a single instance of data. It's much simpler. Therefore, we believe that centralized logging is better for general file I/O. However, centralized logging is not scalable because of coarse-grained logs. So we needed to perform centralized logging with fine-grained logs. There are two challenges. First, how to achieve scalability while using centralized logging. To implement scalable centralized logging, we use per block logging with fine-grained logs. Also, we use log-free indexing data structures to index per block logs. Per block logging is simple. A file is divided into multiple blocks. Block sizes vary from 4 kilobytes to 2 megabytes. Each block has a corresponding log. Each log has a reader-writer log. When multiple threads access the same block, they are serialized by the log. If multiple threads access different blocks, this per block logging can scale perfectly. However, keeping all logs for all blocks consumes a lot of memory space. So we keep only the logs while in use. To index these logs, we use multi-level trees, which reduce memory consumption. We use log-free radix trees as the multi-level tree. The radix tree uses a file offset as a key. To implement a log-free mechanism, we had to use fixed depth trees. This 4-level radix tree can support up to 256 terabytes files, but it causes unnecessary search overhead for small files, so we use a skip pointer. When the file size is small, it can skip unnecessary parent nodes. If the file size changes, libnvmio can adjust the skip pointer. Each leaf node points to an index entry, which is publock metadata. The index entry has the following fields. The entry points to the publock log. The RW log is its reader-writer log. As you know, libnvmio uses differential logging. It logs only an updated part at byte granularity. The offset and length represent logged data in the publock log. The destination field stores the destination where this log will be checkpointed. Since libnvmio uses hybrid logging, the policy field stores whether the log is redo or undo. The epoch field identifies whether or not this log is committed. I will explain in detail in the next slide. libnvmio provides various log sizes. First, the table can be accessed with global, upper, and middle indexes. Each table has the log size of the table. Each size can be ranged from 4 kilobytes to 2 megabytes. For example, when log size is 4 kilobytes, 9 bits and 12 bits are used for table index and offset, respectively. When the log size is 8 kilobytes, 8 bits and 13 bits are used for table index and offset, respectively. This rule can support up to 2 megabytes logs. Since libnvmio uses publock logging, a file has many of publock logs. When an application calls fsync, many of the corresponding logs must be atomically committed, which increases fsync latency. The second challenge is how to reduce fsync latency. To address this challenge, we use epoch-based committing and background checkpointing. libnvmio uses epoch numbers for efficient committing and checkpointing. In this figure, the number in the publock log is each epoch number, and each file has the global epoch number. When a thread performs writing, libnvmio allocates the corresponding log. In that moment, the current global epoch number is assigned to the epoch of the log. In the write operation, the thread acquires the reader log of the pub-file metadata and the writer log of the log. If other threads access the same block at the same time, it's serialized by the writer log. However, multiple threads can concurrently write different blocks. When reading, multiple threads can concurrently read the same block since they acquire the reader log of the logs. When a thread calls fsync, libnvmio acquires the writer log of the pub-file metadata and increases the global epoch number and returns the fsync. If a log has a smaller epoch number than the current global epoch number, it indicates that the log is committed. So libnvmio achieves low latency fsync. libnvmio keeps background thread pool and periodically wakes up background threads. The background threads checkpoint committed logs to the file and then clear the logs. Next write operations allocate corresponding logs with the new epoch numbers. When a thread tries to write, if the thread encounters a committed log not checkpointed yet, the thread first checkpoints the log synchronously. After the checkpointing, the thread completes the write with the new epoch number. In summary, libnvmio provides low latency and scalable file I/O while guaranteeing data atomicity. To achieve low latency file I/O, libnvmio employs user-level I/O, differential logging, hybrid logging, various log sizes, epoch-based committing, and background checkpointing. To achieve scalable I/O, it uses publock logging and log-free Redux tree. In order to evaluate libnvmio on different types of NVM, we used the NVDIMM N-type memory system and an Intel Optane memory system. In the interest of time, however, I will only explain the result of the NVDIMM N-type system in this presentation. We compared libnvmio to various file systems. Xtend4dex, PMFS, and Nova are kernel file systems. SplitFS is a user-level file system like libnvmio. Only Nova, SplitFS, and libnvmio guarantee data atomicity. However, Nova and SplitFS guarantee atomicity for each write operation. On the other hand, libnvmio atomically reflects updated data between F-syncs. In our microbenchmark experiments, libnvmio used Nova as on each underlying file system. First, we measured the effect of hybrid logging. This figure shows how read and undo logging performance changes according to the read-write ratio. Based on 60% read and 40% write, read logging is better in the write-intensive workloads, and undo logging is better in read-intensive workloads. So we used this ratio as a change point for hybrid logging policy. As shown in this figure, hybrid logging can achieve the best case performance of two logging policies. We measured the performance of libnvmio by using FIO. It repeatedly accesses a 4 GB file for 60 seconds in a single thread. We experimented different access patterns: sequential read, random read, sequential write, and random write. All comparison file systems perform file I/O at the kernel level. libnvmio can avoid the kernel I/O stacks overhead, so it provides the highest throughput on all access patterns, outperforming the other file systems by up to 2.2 times. For read access patterns, libnvmio performs only user-level memcopy from the memory mapped file to the user buffer, since it uses undo logging on read-intensive files. For write access patterns, libnvmio updates only the log, not the memory mapped file, since it uses read logging on write-intensive files. When FIO closes the file, the read logs are atomically reflected to the memory mapped file. This figure shows the performance of the FIO sequential write in various I/O sizes. libnvmio performs per block logging but provides various log block sizes. With this feature, libnvmio can keep the high performance across different I/O sizes. The performance generally improves the increased I/O sizes for all file systems, since the number of write system calls decreases within the experiment. libnvmio shows significantly higher performance than Nova when the I/O size is smaller than the page size. This is mainly due to the differential logging. The other hand, Nova uses copy on write for data atomicity, so it increases write amplification on sub-page size data writes. This figure shows the performance of multi-threaded file I/O with the FIO random write. In private file configuration, each thread writes data to each one private file. In this configuration, libnvmio and Nova show highly scalable performance, whereas in shared file configuration, all threads write data to one shared file. In this configuration, only libnvmio sustains scalable performance, while Nova uses per inode logging with entire file locks. libnvmio uses per block logging with fine-grained per block locks. It makes libnvmio achieve scalable performance. We evaluated libnvmio on 4 different file systems by running tpcc with SQLite. In only underlying file system experiments to guarantee data atomicity, SQLite uses each one write-ahead logging technique. Even file systems that provide data atomicity for each operation cannot guarantee the atomicity at transaction level. So in NOVA and SplitFS experiments, SQLite used the while. However, with libnvmio, data atomicity can be guaranteed without the while. SQLite call fsync on commit to ensure that all data updated in a transaction is durable. libnvmio keeps updated data in each logs and atomically writes to the original file when fsync called. So in libnvmio experiments, while was not used. In this figure, running on libnvmio shows better performance than running on only underlying file systems. In the case of kernel file systems, due to the overhead of kernel's I/O stacks, libnvmio can achieve better performance. SplitFS performs user-level I/O, but libnvmio shows better performance, since SplitFS has to perform SQLite while, even when operating in strict mode. As you know, SplitFS provides flexible guarantees. However, even in POSIX mode, libnvmio achieves about 5% better performance. The reason is that SQLite while is inefficient. libnvmio guarantees data atomicity more efficiently than SQLite while. SQLite performs sequential writes to the while file for disk I/O. However, the effect is not great in NVMe systems. While is similar to read logging, when SQLite reads data, it first checks the while file. If no data exists in the while file, then it reads data from the original database file. It incurs software overhead in read-intensive workloads. Since there is only one while file with a coarse-grained lock, there can only be one writer at a time. A checkpoint can run concurrently with readers, but writers have to wait. To checkpoint data, the while file must be synced to persistent storage, and the database file must be synced before resetting the while file. This synchronous checkpoint process affects the entire performance. On the other hand, libnvmio was designed for NVMe systems. It uses hybrid logging. Data can be accessed without checking logs in read-intensive files. Multiple threads can write concurrently. Committed logs are checkpointed in the background. The background checkpointing does not interfere with readers and writers. Applications can easily take these advantages by using libnvmio. I will conclude my presentation. In low-latency NVMe systems, it is important to minimize software overhead. libnvmio is a simple and practical solution. It reconstructs software I/O paths to reduce the software overhead. It runs on any file systems. It provides low latency and scalable I/O as well as guaranteeing data atomicity. In our experiments, it gains up to 2.2 better throughput and 13 times better scalability than other file systems. Thanks for watching my presentation. We will release our source code. We ask for your interest. Thank you.